Yeah, I know, you're just so sick of it. Um, well, I mean, if we need to, we could do one of them, maybe. They were all too easy? That's fine. I was just joking about the easy part. Okay, if we don't, we can do the quiz. Maybe you're thinking the quicker we get done, the quicker you get to go out and frolic in the sun. Okay, well let's go ahead. We'll do the quiz then. So the quiz is just checking solutions. Make sure this works. Mm, mm, guess we'll find out. Okay, I pulled this one out of my files. I just realized I didn't double check to see how it worked, but we'll find out. 1, 2, 3, 4. You're all alone over here. You could join the, or you can, yeah, in the back row. Sure. Here's some. I'll make special delivery. Got it? You got extras. Good. Okay. All right. Good job. By the way, if you are ever sick and you're watching the video, I will always sort of scroll through the quiz, and then you can try it, pause, and try it on your own, and then you can watch the answers magically appear. Oh, homework. I'll get the homework in a minute. All right, hopefully you're coming down the home stretch. You just have to check 3 things. Do your derivative and see what it looks like. So if you are done, feel free to, I'll get the homework first. Don't send it over until I get the homework out of the way. And then I can come get the quizzes. You don't want this? Here. Wow, you sound like a toddler. All right, we're good? Good. Good job. Why? No, it's not. Put some identifying scrawl. You could just put like a ZG or something. Oh, is that what you were going to do anyway? Yeah. Okay. Looked like you did it just by habit. All right, I'll start gathering quizzes because I see they're starting to stack up. So, very nice, very nice. Good job. Good job. Oh, yeah, never mind. I'll come back. You can be last. I know you want to be. He likes to meditate. All right, we're good. What do you think? You like it or you hate it? You don't like it. All right, one more here. You can do it. Good job. Good job. Yeah. You can do it. Yeah. You can do it. You're right. You're doing great. Have confidence in yourself. Good job. See? You did great. All right. You're just meditating? You just don't like the answer? I don't like the answer either. So let's just I'll go get the last one and then I'll come back. No, he likes to meditate on these things. Yeah, you don't like the answer either? Don't worry, none of us do. Yep, good, good. Good job. All right, I think I've got all of them. Any holdouts? Okay, good job. Okay, so yes, no is the answer. Sad, but I'll show you my answers. I fixed the typo though, so that was good. Wait, what is this? Why is that there? Freeze. Oh, that's my after fixing typos. Just a minute. There it is. What's the deal here? Oh, yeah. So I did the derivative, and then I did the right-hand side, and I was like, oh, they're not the same. No. Yeah, that's all you had to do. And then the next one, I had another one. I actually didn't even bother. It's like, no. Yeah. Well, because, I mean, I knew that wasn't going to be the same because of the 2t here. Was the problem? I don't know. Yeah, because I would get 2 times 2t is definitely not 2t. So I was like, no, it's not going to work out. And also the t squared wasn't going to we weren't going to get rid of t squared. The third one, I was hopeful, but it was also a no. So I should have asked you a bonus question. Could you come up with one that was a yes, which I'm pretty sure some of you could, but so this one's a no as well because they don't match. And so the yes wasn't too difficult. You kind of working with the building blocks. I don't know if anyone here can figure it out, but here it is. Here's a yes. So this one works. And I added it as a 4, but so just so you know, there was a typo apparently somewhere. I pulled this out of my files though, so you can blame myself from 4 years ago. And then not me this year. So that should have been a 2. Doesn't matter. If you got no, you're good. So you're doing a great job. Okay, so today we're going to be doing, it's similarly relatively easy, I think. And that is just to introduce the idea of initial value problem. An initial value problem is how we get solutions for specific problems. I think, as you probably saw on your homework, that we have this idea of a general solution And so the general solution tells you like this whole family of solutions, and all we're going to do is narrow that down to a specific solution that we're interested in. Here's an example of an initial value problem, and eventually you'll be able to solve this the way I'm about to, but for now you'll just have to trust me that y is equal to some constant times e to the 2t is the one parameter family of solutions for this particular differential equations. So that's the solution. In fact, all of your homework, you're given a differential equation, a general solution, and an initial value, and you're supposed to figure out the constant. This is similar to what you did in Calc 1. Do you remember computing values for C in Calc 1? Well, we're going to do the same thing here. That's all this is. So if you can do that, we're pretty much done. We'll show you a few pretty pictures, though, before we go. So let's actually do this. When you see something like this, this means that t is equal to 0 and y is equal to 3. So 3 is equal to c times e to the 2 times 0. So that means that c is equal to 3. And my final solution to this initial value problem is 3e to the 2t. Done. So eventually, so down the road, next week actually, you're going to learn how to solve equations like this. You'll get a general solution. The general solution is the one with the c in it. All we're doing today and for homework is, so it's super easy, it's going to be happy day tomorrow, right? Is practicing the idea of taking a general solution, doing this, to come up with the particular solution. So this is a particular solution. That with the c in it is a general solution. So the difference between these two is this, that if you have a general solution is sort of a family of a bunch of different solutions like this. But once you have an initial value, like this x0, y0, then you've nailed down which of those solutions that you're interested in. Now, in addition to having an initial value and having a solution, you're going to be also at times interested in an interval. You see, this solution might only be true for a particular interval. You'll see this in just a minute. We'll see some examples where you'll have solutions that are only true on a certain interval. But this picture pretty much says it all. General solution is everything there. Particular solution is the one solution that goes through the point that you're interested in. Okay, so let's see, we already did that. Okay, here's another one. Let's just do another one just to see that there is a variety of these sorts of things. So this is the same one parameter family, is it? Yes, it is. This is the same one parameter family that we had earlier. So this is c e to the t. So I'll give you a minute. Go ahead and see if you can come up with the value of c. Find the particular solution that goes through the point 1, e. I'll give you a minute. It's not too hard. Okay. Let's find our randos. Randomize. All right, Joshua, you're up first. What do you think? How am I going to find C? Or did you just find C? All right, what do you got? C is 1, yeah. C is 1. And if you're not as quick as Joshua, you might say, okay, how did we get that? Well, y is equal to e when t is equal to 1. And then you're like, well, wait a minute. C times e is equal to e. That means c has to equal 1. So sure enough, the particular solution we're interested in here is e to the t. Now, of course, it can't be this easy all the time. So let's make it just a little bit more difficult. Not terribly so, just a little bit more difficult. And by adding one more sort of additional feature, we're gonna make it just a little, not terrible, don't worry. So in these are first order. So this is first order differential equations. That's what we've been doing up until now, just the first couple of problems. That's this picture, by the way. First order differential equation, you have a family of solutions, and you're just picking from among that family. Which of those do you like the best? Ah, that one right there. So here's the picture that is associated with that. Here's some solutions, pick the one you like. Well, second order differential equations, which are more useful, to be honest, in especially for you engineering people. The second order differential equations are a little bit more complicated. So a second order differential equation is it ends up, you end up having two pieces to your initial condition. I'll show you an example here in just a minute. But here you have two things you have to worry about in order to solve a second order differential equation for a particular solution. And so usually there are different ways that this could happen, but usually what you'll have is you'll have like this, you'll have a point. So that's what this is. It tells you where to find your solution. So kind of like this, we're going to go through that point. That's like your initial value. But you also end up with another piece of information, usually something like this, that tells you the initial slope. So that's what that is. Y prime is slope. And it just says, okay, the initial value of this is y0 and the initial slope is y1. So when we're dealing with something like that, you might have something like this. Now, this isn't a complete picture in the least, but you would have all of these solutions, and the solutions would be all over the place, this crazy, thing that, all sorts of different solutions. But you would first of all figure out where you want to be, and then figure out the slope you want, and then that will narrow things down to the solution you're interested in. Of course, we're not going to do this using a picture. We're going to do it using algebra. So let's take a look at an example of this. Oh no, this is the easy one again. Okay, this is the easy one again. I just wanted to show you how the picture looks. So here, if y of 0 is equal to 3 for this, you have y is equal to 3e to the x, and that's this solution right here. So this is a one parameter family, a first order. We'll get the second order. Is the second order next? Yes, it's next. Sorry. And then this one, let's see, y is equal to, y of 1 is equal to -2. Okay, I guess I'll have to actually solve this. -2 is equal to c e to the 1. Okay, so c is equal to -2 over e. So -2 over e to the x. And that's this right here. So you can kind of see that all of the solutions to that differential equation are going to look like this. They're different exponential functions, either going up like this or going down. And then you just find amongst all of those solutions the one that goes through the point you're interested in. Nice and easy for a single parameter family of solutions. For a two parameters family of solutions, things are a little bit harder. So let's take a look at this. So suppose you know that, and once again, we're going to get to the point where you're going to be able to tell me what the general solution to this is, but for now you'll just have to do your best or just assume that it's going to be given to you. So cosine of 4t plus c2 times sine of 4t. And we're told that I want the solution that goes through this point, that when t is equal to pi over 2, x equals -2, and at that point the slope is 1. Well, we certainly can just plug in pi over 2 to figure out, well, let's see what happens when we plug pi over 2 into this. So let's use this thing first. So to use that thing, we know that when x equals -2, t is equal to pi over 2. So I've plugged this pi over 2 in for t, and I've just changed the x to -2. So that's not too bad. Well, hopefully we know what the cosine and sine of 2 pi are. 2 pi are, yeah, I guess it's plural. So, well, do you know what the cosine of 2 pi is? That's a good one. The cosine and sine, which one is 1, which one is 0? Do you remember? You can take a guess. It's good to know. Yeah, the cosine is 1, that's right. So this is going to be 1 here, C2 times 0. Oh, well, that's easy enough. That means that C1 is -2. Now, the problem is that I don't know what C2 is. To figure that out, I'm going to use this piece of information here. And to do that, I need to find the derivative. So you've got the function over on the left. Let's get the derivative of that function. So let's see, Luke knows what the derivative of cosine of 4t is, don't you? Yeah, we can put that in there. Did you say 4? Oh, yes, you're right. Okay, sorry. You're doing better than me. I was just going to leave it as C1. No, I like it. I like what you're doing. So let's actually do that. Let's do what, so change this to -2. There, that's way better. I like your style. Okay, so this is going to be 8 sine of 4t. I like it. Good job. Okay, now this C2, we don't know what C2 is. That's our goal. But Rachel J., you know what the derivative of sine of 4t is, don't you? Yeah, okay, so 4C2 cosine of 4t. Good job. Okay, so notice that once you have your function, your solution, general solution, you can come up with the derivative of the general solution. From here, we can plug this in. So now we've got this that I can do. So notice x prime is 1 sine of 2 pi plus 4C2 cosine of 2 pi. So you see how I did that? Got that figured out? And now we're just going to have to know our sines and cosines. So this is 4C2, which means C2 is 1/4. So here's the final solution. Let's put it all together. X is equal to -2 cosine of 4t plus 1/4 times sine of 4t. Okay, so this was a little disappointing for me, to be honest. So we're going to have one more before we get to existence and uniqueness, because that one was too easy. So let's go make one that's just a little bit, not too much harder, just a little bit harder. Don't fret. So let's see, let's zoom out just a bit. Okay, so let's try this one. How about this? Let's see, d squared y over dt squared plus 3 dy over dt plus 2y is equal to, we'll make it 0. Just make it easy on myself so I don't have to think too hard about this. So here's my differential equation. I'm going to have y of, let's see, 0 is equal to 5, and y prime of 0 is equal to -1. Let's go with that for my initial value and initial slope. And I suppose, like I said, eventually, actually it will be about 2 weeks from now maybe, you'll be able to look at that and do what I'm about to do and just write down the solution. This one is a super easy one. Y of t is equal to C1 e to the -t plus C2 e to the -2t. So eventually you'll be able to do this super easy, this particular differential equation. But for now, you're going to just trust me that this is the general solution, and you're going to pair that with these two. See if you can figure out the values of C1 and C2 for this 2-parameter family of solutions. I'll give you a minute. Do the algebra. This one's a little bit more complicated than the last one, even though this one doesn't have sines and cosines. All right, well, let's just get things set up so that we know that we're on the same page. So Madison, what do you get when you plug 0 into this thing for t? Well, you're plugging 0 in for t, right? And this one's y here. Yeah, so it's e to the 0. Very good. And then c2 e to the 0. So I end up with this equation, c1 plus c2. So this is why this is a little bit more complicated than the last one. We ended up with an equation, 2 unknowns. So I can't just nail down an answer for c1 or for c2. So we got lucky with the last one. This one, not so lucky, but it's okay. We'll be able to overcome it in just a minute. So the way to overcome this is we're going to have to compute the derivative, y prime. So someone will need to come up with a derivative, and who is that someone? Tyler's that someone. Tyler, you know the derivative of y, the purple y up there.
Negative c1 e to the negative 2 minus 2 times c2 times e to the negative 2.
Beautiful. Okay, so there's your derivative. And now you can probably guess what we're going to do. So we're going to take this and stick it in there. Okay. And then you'll be able to solve 2 equations for 2 unknowns. So take a minute and do that. I guess let me just, well, I'll just write it down. This is negative 1. This is negative c1 e to the 0 minus 2c2. All right, let's see how we've done. I don't know if you have your favorite method for solving 2 equations, 2 unknowns. Personally, I like elimination because I just like the way it sounds. So that's what I'll do. To eliminate, you just add these together because these 2 are going to, the C1s go away. But normally you would have to rearrange or multiply by something so that the coefficients lined up. But I'm just going to add these two things together. And that's going to give me the following. 4 is equal to 0C1 minus C2, which means that C2 is equal to -4. Does that sound about right? Okay, so C2 is equal to -4. Now you can use whichever equation you'd like to come up with the other number. So I'll use the first one. 5 is equal to C1 minus 4, which means that C1 is equal to 9. Now we have our final answer, and that is that y is equal to 9e to the negative t minus 4e to the negative 2t, and that came from the original general solution. So this is a general solution, and down here, this is a particular solution that matches all of the initial conditions, however many there are. In this case, there's 2. Second order, by the way, there will be 2 initial conditions. If it was third order, you would have 3. Fourth order, I don't think we have anything beyond fourth for any of our applications. So there's an application with a fourth order differential equation, but that's as far as things go. So what do you think? Does it look pretty easy? You can do this yourselves? Okay, so there's one last little thing that we have to talk about. Actually, 2 last things. Yes, good. So we have 2 last things that we have to talk about. First one is kind of it's not a triviality, I shouldn't call it that. It is something that is important to note, but that we aren't going to dwell on in this class. And that is that there are theorems that describe when a differential equation has a solution and when that solution is unique. So existence it answers the question, does the differential equation have a solution? So in other words, do any of the solution curves, do they pass through this point? That's the thing that we would like to know. And then the second thing, uniqueness, asks when can we be certain that there is precisely one solution curve passing through that point? So this one is the more interesting one to me, only because this one can be answered by just solving the differential equation. If it has a solution, you'll be able to find it. The second one, the uniqueness thing, is the thing that is kind of interesting, because there are certain situations where you don't have just one solution. There might be more than one. So I wanted to show you an example where you don't have uniqueness. And I've got the theorems on one of these slides, but I wanted to show you this situation here. So here we have a differential equation. dy over dx is equal to x times the square root of y. So here I'll just write it like this. dy over dx is equal to x times radical y. And this initial condition. So take those 2 things together. It turns out that there are 2 solutions that match that initial value problem. In fact, this one, y equals 0, you can double check. What's the derivative of y equals 0? Derivative of y equals 0 is 0. And if you plug y equals 0 into this, you get 0. The other one, which is the more interesting one, is this one. So you can double check this. The derivative of that is 1/4. Maybe I'll write it like this. 1/4 times x to the 3rd. And if you take that and stick that into here, this is going to take a little bit more effort. dy over dx should equal x times the square root of 1/16 x to the 4th. So let's check to see we'll go back. So this is dy over dx. Does that equal x times 1/4? Doing the square root x squared. And indeed it does. 1/4 x cubed. Notice that these are the same. So that's a solution. Both of these are a solution. They both go through the same point. This is not something that happens routinely, but it does happen here. What this means is that if you have a solution, if you're trying to, I guess this is the issue that we will run into. If you're solving this differential equation and you have a like an actual physical problem that you're solving, and if that solution is y equals 0 for whatever reason, then when you get to this point, 0, all bets are off. So whatever the situation is, you have some physical problem that has this solution, y equals 0. When you get here to 0, 0, you might end up on this other solution. In fact, there's actually an infinite number of places you could go from here, but that's not to worry about that right now. Maybe a better way of looking at it is if you're on this solution curve and time is moving forward and you get to that point, we don't know where you'll go from here. It's like something weird happens and you might end up somewhere else. So you might be on the blue curve or the red curve after that. So there's at least 2 solutions that go through that point. There's actually an infinite number, but that's, like I said, we'll not worry about that too much at this point. So why would that happen? And how can we prevent that or avoid these sorts of special points? Well, here's the uniqueness, the existence of a unique solution. So it's a little bit wordy, but I'll explain it, and we'll look at a pretty picture to see what it means. If you have a rectangle of a region that contains the initial value, so this point here is the initial value. If the function f of xy, this is, for the derivative differential equation, differential equation. I should write it like this. So you have this differential equation, y prime is equal to f of xy. So just to orient you, this is kind of a theoretical result. So we don't do a lot of theoretical results in here, but some of them are kind of interesting. So we'll stick with the interesting ones. So just to go back here, this one, the f of xy is this right here. It's that thing to the right. So we're just dealing with first order differential equations at this point. So if you have this differential equation, if this function and the derivative of that function with respect to y are both continuous, then there exists some interval. Don't worry about the notation there. Just think of it as an interval that is contained in this rectangle where there is a unique solution. So this speaks to both existence and uniqueness. So all that is saying is that as long as this function is continuous and its derivative with respect to y is continuous, then you're going to have a unique solution that extends to some degree on either side of this point. That's all it guarantees. It just says there will be a solution and it will be unique. There will be only one solution. It'll be important later on that we know this because we don't want weird things to happen. Like if you throw something across the room, we don't want it to magically change position or change velocity without following the rules of physics. So getting back to this, so what went wrong back here? Well, let's clear all this ink so we can see. Here is the function that we're interested in. So let me write that down. F of xy is xy to the 1/2 power. So we need to ask ourselves, is that continuous? Well, it is continuous, but not everywhere. This thing is continuous when y is greater than 0. So you might say, well, what's going on with y equals 0? Well, if you think about it, y equals 0, there's a discontinuity because when y is less than 0, this is undefined. So there's a discontinuity. Now, as long as we've got this up here, let's take a look at the derivative of this thing with respect to y. And if you haven't had multivariable calculus, that fancy D just says do the derivative with respect to y of this. So this is going to be 1/2 x times y to the negative 1/2. Here again, we have a situation where this thing is continuous for y greater than 0. But it's discontinuous at y equals 0. In fact, when y equals 0, you have a big problem, don't you? You plug y equals 0 into this thing, and it's undefined. You have 1/2 times whatever this x is times 1/0. So what this is telling us is that as long as you stay above the x-axis all of this, you're going to be unique. Your solution will be unique. It will be defined. You'll be good. Once you hit y equals 0, all bets are off. We don't know what's going on with the solution. It's not unique. So not a huge deal. And we're not going to dwell on some of these theoretical matters as much as it seems like we are. But it's just kind of an interesting situation. So here, this is all laid out here. So in the homework for Friday, you're going to just have to deal with initial values, very similar to today's homework. So let's see. I think that the main, let me see, I have this here. I don't know if I put it on. Oh, I don't have it here yet. I have it in the book, but the one thing that is, well, I don't know. I think you're going to be able to handle this. So there's one section, the very last section is a multiple choice section where you're supposed to choose amongst different solutions based on initial values. You're given some solutions. I think you can probably handle it. Just pick the one. So these you're not going to compute. You're just going to pick the one that makes the most sense. Okay, so I think that's actually all that we have here today. So we're done a little bit early. That won't normally happen. I always feel bad when we end early. I know that it makes you feel good. So you have time to go frolic in the sunshine. But if you do have questions, stick around.